A very good morning to all of you. I welcome you all for this engineering thermodynamics course. So today's classroom discussion topics are to derive the difference in heat capacities, derive the ratio of heat capacities, and define coefficient of volume expansion, and also define the isothermal compressibility factors. So the motivation behind these particular topics are very important one. So it is important to know the equations for difference in heat capacities, ratio of heat capacities, from which important relationships among the various thermodynamic properties can be determined, which are very useful in solving the numerical problems, and coefficient of volume expansion and isothermal compressibility factor parameters are defined from these equations. And the lecture learning outcome from the today's class is, so you should be able to analyze the applications of the equations for difference in heat capacities and ratio of heat capacities. So in the previous class, we derived the Maxwell relationships and the TDS relationships. So now, based on that particular the TDS relationships and the Maxwell relationships only, we are able to derive the difference in heat capacities and the difference in, ratio of heat capacities. So let us just go through here. So it is our first TDS equation and it is our second TDS equation. So whenever you are equating the first and second TDS equations, so we are able to get like this, that is 11.10. Just by substituting all these things, we are able to get Cp minus Cv is equivalent to minus T into dou V by dou T with respect to P whole square and a dou V by dou V with respect to T. And this particular equation is very important one, because what is the importance of that particular difference of heat capacities? So what actually we are retrieving from that particular equation? So that is, analysis is very important. So whenever you are going through the analytical part of the difference in heat capacities, so here I have written the four important parameters. So from this particular the four important parameters, so we are able to get it. Cp minus Cv is equivalent to R. That is a very important one. That is, the difference of heat capacities is always giving us the characteristic gas constant value. That is, the Cp minus Cv value is always equal to R. So that we are able to derive from the difference of heat capacities. So it is only possible because of the Maxwell relationships and the TDS equations. And from this particular difference of heat capacities equations, that is equation 11.10 here. So go to the equation 11.10 because it is the basic equation for the difference of heat capacities. So from this particular 11.10, so we are able to analyze the four important conclusions, and from that equation 11.0 we are able to define the another important parameter, that is the volume expansivity, so which is normally denoted by beta. So beta is equivalent to 1 by V into dou V by dou T with respect to P. So it is known as the coefficient of volume expansion. So because in the lecture level outcome also, I've already clearly mentioned that, so you should be in a position to define the coefficient of volume expansion as well as isothermal compressibility factors. So now the first part is over. It is from the basic fundamental equations of the difference of heat capacities. And similarly, the another parameter also we are able to define from the previous equation, that is isothermal compressibility factor. So from the isothermal compressibility factor, it is Kt. It is the notation to express the isothermal compressibility factor. So Kt is equivalent to minus 1 by V into dou V by dou T with respect to T. And whenever we are substituting this particular the values, so then the equation 11.10 can be expressed as Tv beta square by Kt. That is, the difference of heat capacities is always equivalent to Tv beta square by Kt, where beta is equivalent to coefficient of volume expansion and Kt is equivalent to isothermal compressibility factor. So this is a important equation for the difference of heat capacities, so that we are able to analyze the several parameters from that equation. So coming to the next part of this topic, it is to find out the ratio of the heat capacities. That is, we have to derive the ratio of the heat capacities. So once again, the basis is from the previous, the Maxwell relationships and the TDS equations only. So here at constant entropy, the two TDS equations will become, so it is the first TDS equation and it is the second TDS equation at constant entropy value. So from that particular one, so we are able to derive that Cp by Cv, it is equivalent to gamma. So that is the ratio of two heat capacities is always equivalent to the adiabatic index, and this value for the air, it is equivalent to 1.4. And in the previous slide, we have defined the coefficient of volume expansion as well as the isothermal compressibility factor. Now we are able to define the another third important thermodynamic parameter, that is adiabatic compressibility factor. So adiabatic compressibility factor, it is minus 1 by V dou V by dou P here with respect to S, that is adiabatic compressibility factor. But whereas in the previous isothermal compressibility factor, so here you are able to see, so it is with respect to T. So that is the only difference. So it is with respect to temperature, it is isothermal compressibility factor, and whenever you are defining with respect to the constant entropy, that is the adiabatic compressibility factor. So Cp by Cv is equivalent to gamma, that is the ratio of heat capacities, where gamma is equivalent to what? So gamma is equivalent to Kt by Ks. So Kt is nothing but isothermal compressibility factor and Ks is nothing but adiabatic compressibility factor. So here the very important relationship among the adiabatic index, adiabatic compressibility factor and isothermal compressibility factor, which we are able to derive from this particular equation. So that is the ratio of two heat capacities is always leading to adiabatic index, and always this particular the adiabatic index, it is the ratio of isothermal compressibility factor to adiabatic compressibility factor. So that is very important one. So it is the basic idea about the derivation of the difference in heat capacities, and similarly the ratio of the two heat capacities. So with this we are able to define the coefficient of volume expansion, isothermal compressibility factor as well as adiabatic compressibility factors also. I hope this particular lecture is very useful to you, because it is only the derivation part. So it is a mathematical part is involved. So practice it. So whenever you are practicing, then only you will be familiarized with the derivation part of the difference in heat capacities and the ratio of the heat capacities. So thank you one and all for attending and listening this lecture on the difference of heat capacities and ratio of the heat capacities. Thank you one and all.